lecture 8, and first of all, thank you for submitting your homework number 7, and I check your homework submissions, and if you fail to do so, then please remember this one. We have the specific language for this application, so you must follow the grammar it assumes. For example, it has certain uniform grammar like this statement, and here we have a normal parenthesis, and this one has a spec, and here we have curly bracket, and here we have body. So in order to properly perform our simulation, actually you must distinguish this parenthesis and this curly bracket. If you use parenthesis when you have to grouping this body, then it will generate some errors. So therefore, please follow this kind of the convention properly. And another one is, so if we have a rectangle, if that is the name of a statement, then you must follow that name. So you cannot just simplify it like RECT. It's not the way for working in this code, because this one has very strict grammar, because I have limited development capability, and so everything is just fixed. So please, if you fail to do it, then please try again, because this course requires for you to do this job very continuously. So if you fail perform this lecture 7 homework, then you will fail again and again. So please, if your submission was not that successful, then do not give up. So if you give up here, then your entire semester is over. So please try once again homework number 7 and get the right implementation. Okay, so if you have done it quite well, then congratulations. But if you have not, then please try. Do not submit the unfinished homework to me, because as I told you before repeatedly, this lecture is just a one-time lecture. This is a special topic, and it will not be given to you as its present form. So although its contents can be reused as our regular lectures with a different name, but this is only your time to attend this course, special lectures on basic ECS. So you should not fail this course. Okay, so therefore already lecture homework 7 reveals that some of you guys fail to follow the lecture progress, but it makes serious problems your final credit. So please follow the lecture progress. Okay, so that was my feedback to your homework number 7. So my final, once again, comment is, please do not give up. So this is very initial stage of our lecture course. So if you give up here, then it's over. Okay, lecture 8. We are now talking about lecture 8. And when we go to our previous lecture content, lecture 7, then we can find this final structure. So this one shows this is corresponding to yes, this one is corresponding to the substrate. This is a silicon, and we wanted to make fins in this part, and here we have a pad oxide, and here we have so-called hard mask. Usually it is made of silicon nitride, and here we have the layer of so-called mandrels, and this yellow one is actually typically amorphous silicon. And as you can see here, you have green ones, which is basically sidewall attached to this patterned mandrel layer, and this is usually done in silicon dioxide. Maybe you can find that we have intentionally introduced different materials for different layers, and maybe you can ask me this question. Well, this sidewall, the sidewall attached to the mandrels and pad oxide, both of them are the same silicon dioxide. Yes, we have the same silicon dioxide here and there. However, they are well separated by this hard mask, so we can separately use them. So in this case, well, the role of mandrel is over. It was used as to make this sidewall, and now it should be eliminated. But if we try to eliminate this mandrel, but we have to keep this sidewall as before, so that should be done in this course. Well, we have on top of this structure, we have silicon nitride, silicon dioxide, and amorphous silicon. But we wanted to eliminate only selectable region, so that should be done by this one. Here, previously, when we wanted to make a certain selectivity for spatial selectivity, we introduce a specification or statement called as a mask. Mask defines certain rectangles, and these rectangles are saved from its etching process. So, however, using just a mask, it doesn't make any consideration about material, or region-wise consideration is not provided by this mask. So instead of this mask, now we have to introduce material-wise selectivity. So that's the reason why we introduce a different statement called as model. So also it should have a name. Once again, this one is spec, and in this grammar, this is body. So for example, if you write down in this way, obviously it will generate an error. And if you place this name part into your body, of course that will not be respected. So please follow the grammar of this Armstrong-Crafts, this code properly. And anyway, now we have the name model underscore fin, and you can define many of them. And here we have the body corresponding, setting the selectivity. When you just make this model, no material, actually no region is selected. So in order to make something effective to certain region, then you have to call this body select, and region name is specified. So here it means that amorphous silicon is selected. If we do this etching process without any kind of a model selection, and that will be the answer or the resultant profile of our etching process. Please make a comparison. Starting from this one, I wanted to delete this yellow line corresponding to mandrel. So if I just introduce a certain anisotropic etching by amount of this mandrel height, then also this part corresponding to silicon nitride or hard mask will be also etched away. That's the reason why when you have a look at this form, your form just looks like this. Then does it give us a certain pitch corresponding to 27 nanometer? Actually not in this case. So if we consider pitch between these two structures, then pitch is given as the original one, 54 nanometer. The magic, we can have 27 nanometer out of this 54 nanometer pitch is now these side walls have pitch of 27 nanometer. So simply speaking, we must do selective etching of this mandrel layer only. Then now what you can do is like this. So usually we have done in this way, etch and thickness equal to 50. Then this structure from top, the 50 nanometer is gone, and that was our previous result shown here. However, if we specify the model which says that only amorphous silicon should be etched, then what you get is now this silicon nitride is not affected by this etching process. Also, this silicon dioxide is saved from this etching process. Only previous, the one filling in this part, mandrels are gone. Now you understand, now our pattern, it has the pitch of 27 nanometer and 27 nanometer. That was possible by using this selective etching. Now remaining thing is this one. How can we make this kind of a selective etching? Which one can provide us quite a good etching rate for only for amorphous silicon? At the same time, no etching for our silicon dioxide, it is saved. And how about this is silicon nitride? Maybe it seems like a magic or just an assumption that there exists a certain material or certain etching process to do that. So here I introduce the representative way we do it. So actually this is my first time read this name, so I'm not the experimentalist. I'm just working in modeling and simulation. So usually I do not have a proper understanding on what is chemical actually used, and I just dig out the references and I found it. So this is a tetramethyl ammonium hydroxide. Well, what is this? This is the form of this TMAH, tetramethyl ammonium hydroxide. And here this part, and here we have another part. This part is corresponding to OH minus, and this part is corresponding to tetramethyl ammonium. So usual ammonium has the form of NH4. This is the chemical formulation of usual ammonium. However, instead of this hydrogen atom, we introduce methyl to the place of this hydrogen atom. So what is this? At the center of this structure, you can find a certain blue ball, and this blue ball is corresponding to our nitrogen atom. Here we have a nitrogen atom, and it has four for bondings, and that is each of these bonding is connected to this methyl here and there. Now we have this kind of chemical etchant, and when we insert it into our system, and of course we have to provide a certain heat, specific temperature is required. In this case, it is known that it has different etch rate for different materials. Here we have a silicon, and it has the face, a surface, and in this case, per 1 minute, it can etch 500 nanometer. 500 nanometer is corresponding to 0.5 micrometer. This is huge. And in the case of silicon nitride, it is virtually zero. It is not damaged at all by this chemical etchant. And how about silicon dioxide? It is not exactly zero, but its number is 0.2 nanometer per minute. If you wait for 1 minute, but it is just etched away by amount of 0.2 nanometer, so only one single layer or less than one single layer is etched by this chemical. Of course, I have to stress that this is for crystalline silicon. And if we have a look at different numbers like 110 or 111 direction, it has a different etch rate for different surfaces. So we cannot say that this is an isotropic etchant for crystalline silicon. But anyway, our mandrel is usually made of amorphous silicon, and as an experimentalist, you can just repeat your experiment to estimate the etch rate of your mandrel layer. Point is, etch rates shows completely different orders between these three materials. Silicon nitride is perfectly safe, and even silicon dioxide is not affected by this chemical etchant. So therefore, if we can find a certain number, suitable number for amorphous silicon, then we can just calculate the correct time duration for this etching process. Then we can completely remove this mandrel selectively. Okay, so are you with me? So that is the one. So maybe in this lecture, I will repeatedly show you there is some way to selectively etch only silicon, or selectively etch only silicon dioxide, or selectively etch only silicon nitride. So it seems like a magic. However, behind the scene, we always have the practical way to etching selectively these representative materials. So this is just one way, one example of selectively etching only silicon and keeping our dielectric materials. Okay, do you have any question about this one? So fortunately, so who invented this one? I have no idea. This is just collected information from long time investigation. So now we have a certain toolbox for this material selection. If you want to do such kind of etch rate, then you can just watch the toolbox and select the proper material, then you can make good selectivity. Okay, so now it looks perfect, and we have finally a fin pattern which has 27 nanometer pitch. Hooray! But unfortunately, this is just silicon dioxide layer, And what we have to do is actually transfer this pattern into our silicone substrate. That is required in our case. So simply speaking, if we talk about fin formation, if we just roughly speaking, okay, please make a uniform fin, but it is not that easy. In order to make uniform fin onto the silicon substrate, we have to first do this kind of complicated jobs. We cannot make a simple block stacking to make this fin formation, because what we can do is only from doing something on the surface from top of our wafer. So we cannot make it from the surface of our structure. We cannot build selectively something. So that is the problem. So that's the reason why we have to spend quite a lot of time on this one. So maybe then how can we do that? One, if we say this one, silicon dioxide, then why don't you just drill down? Then if we just drill down this structure entirely, then maybe we can find, well, no, using this opened area, this part is open and this part is open. Using this open area, if we can drill down quite exactly, then we will have the fin here. We have a fin and we have a fin. So that is the ideal case, but unfortunately it is not the realistic case. So that's the reason why instead of this silicon dioxide, here we have a hard mask. And first of all, our pattern made in this silicon dioxide layer is first transferred to this hard mask layer, and only after that, using this hard mask layer, then silicon is patterned. So why? So I have a little idea about that, but according to the references, it is closely related with stability of materials. So we have to do, in order to perform this kind of deep etching, then our this guy should keep its shape as much as possible. However, unfortunately, this silicon dioxide layer is not strong enough till the end of this etching process. So what we do is first transfer our pattern into hard mask, and as the name says, hard mask, this hard mask resin is one of the strongest one, which against the etchant for most etchant. So that's the way we do for this fin patterning. So let me just show it to you. So in order to do that, so what we do is spin coat a layer of a photoresist. This is nothing related actually fin patterning. However, we need this another patterning related with photoresist, because I will just show you the sorry. Okay, here we have it. The final structure we wanted to have looks like this, and here you can see certain lines corresponding to fins. These are all fins, and that is our target structure. But you can find that even for this fin structure we have two different colorings. One is gray one, and another one is this green empty box, and once again this gray one. So simply speaking, we don't want to have these fins in this part, so we wanted to eliminate these fins. So that's the reason why we have to do once again this patterning. So let me just stop here. Here we have introduced once again the spin coating of photoresist, and it means that when we introduce photoresist, it is directly related with another exposure. Then why we have to do that? So selectively keep this fin pattern, and for other part we wanted to eliminate this one. Although we try to our best to have this fine structure with 27 nanometer as much as accurate as possible, but for unwanted reason we have to remove them once again. So that is the one. Then how can we make this spin coating? And unfortunately we don't have some comment in Armstrong craft like spin coat something, so there is nothing. So although it is not the real deposition and it is not the real CMP, but please just follow these two lines. Just to deposit a new layer called as a photoresist sufficiently enough. Actually this thickness is not that important, so you can just thick enough one, and after that you have another one called as CMP, chemical mechanical policing, and you can just specify position. So please note that this position is its z directional coordinate, so always normal to xy plane. So you can easily understand this position is corresponding to the coordinate equal to z equal to 303. So if you say, oh, I don't like 303, so I wanted to have, for example, instead of this number, if you say just 300, then what will happen? Then your final result will a little bit shorter than present one by amount of 3 nanometer. You can precisely select the top of your structure. Okay, then one question is, then how can we select this number? This number seems to be too arbitrary, 303. What does it mean? So my calculation was like this. Including this silicon substrate, it was 100, and pad oxide thickness was set to be number 3, and if you remember correctly, the thickness of our hard mask was 80 nanometer. I think that 80 nanometer hard mask is a little bit thick in our case, but anyway, we started from 80 just to keep it. Then please try to the coordinate at the top of our hard mask layer. It will be 183, and you have just spin coated the thickness of 120 nanometer thick your photoresistor. That's the reason why I selected it 303. Then of course you can ask me this question: why did you select this thickness as 120? I just dig out the references and find that maybe 120 is a reasonable number for this one, but I have a little idea about that. So actually the thickness can be controlled quite well. For example, if you pour your photoresist onto the vapor, after that this spin coat means that the vapor itself is rotated. So that's the reason why it is called as spin coat. Photoresist is coated. Yes, it is uniformly covered over our existing structure. However, how can we do that? By spinning, by rotating our vapor with quite a high speed. Then we can, as a result of this, because usually photoresist is a liquid phase, in its liquid phase. So if you just make a quite a fast rotation, then it just spread over all your vapor quite uniformly. That's the reason why we can assume this quite a flat surface for our spin coated photoresist. Then who decide this thickness? Of course, the amount of you first give onto the vapor determines the total amount of photoresist, but at the same time the speed is important. If you spin quite fast, then there is a tendency that your thickness is reduced. Of course, so you give something and just rotate it, and some of them will just escape from that vapor top surface, and remaining thing is quite flat. And if you rotate it quite slow rate, then nothing will escape from your vapor. Then you will have a quite a thick photoresist. So if you are an experimentalist, then you can actually perform many experiments to find out the final target thickness of your spin coated photoresist. So we assume that we can do it. So that's the reason why we know the thickness of this photoresist layer. Okay, then now you may feel that, oh, we spent quite a lot of time to make this fine pitchy lines, but it is once again uniformly covered by photoresist. So we just lost the patterning. Yes, you are right. Right now you have this condition, but please note that this is a photoresist, and here you have still silicon dioxide. And if we have sufficiently good material selectivity, then we can recover this pattern anytime we wanted to have. Okay, so what we have to do is like this. Now we have to define so-called active regions. Actually, here we have two active regions, and one is for this relatively top one is for our later P MOSFET, and here we have one corresponding to our later N MOSFETs. So we will introduce two rectangles here, and it has 2 point x0, y0 and x1, y1, and they are corresponding to 2 points here. So why don't you just point out those numbers? 27, 36, that will be corresponding to this point, and 135 and 117, that is corresponding to that one. So we are specifying this N MOSFET well part, and another one, this top one is corresponding to these 2 points. So now these two rectangles are saved from our later etching process, or more precisely our exposure. Light exposure is saved for these two rectangles. After that, for other parts shown here, these parts, and light is exposed, and now our PR becomes quite weak against this etchant. Then by washing, then they are gone. So now we have still remaining quite strong unexposed PR, this part and that part, and for other parts now our silicon dioxide pattern is now exposed, and of course this one is corresponding to hard mask. Then now we have, from the top view we can find three different materials. One is PR, and other one is silicon dioxide, and another one is a hard mask. And what we do is now okay, so I think that what we have to do is etch silicon dioxide and silicon nitride selectively. Then you can ask me this question, well, how can we etch only silicon dioxide and silicon nitride selectively? PR usually is an organic material, so is there anything which can resist against this etchant? Well, silicon dioxide and nitrides are attacked and damaged, but PR is just remaining. Usually what we have is PR is regarded as a certain sacrificial layer. So although PR is damaged and etched away, however, as much as they protect the remaining fin pattern or silicon dioxide or nitride pattern, it's okay. We don't care about the full recovery or full health of our PR layer. PR can be sacrificed quite easily. So then what we can have in this case is like this. Please have a look at this one. In this case, I assumed quite a strange assumption. The one is, well, our photoresistor is not affected or not etched entirely. No damage on our PR. So active region, where is the active region? This one is the active region for MOSFET, and this one is the active region for PMOSFET. They are perfectly kept. And for other part, we have exposed silicon dioxide or exposed silicon nitride, and of course when we make a certain etching process, silicon dioxide and silicon nitride may, and in reality they have, different etch rate. So the usual choice is the material which has a higher etch rate for silicon dioxide and lower etch rate for silicon nitride. Certain selection is made. So then please think about what will happen. So now when we start this etching, so then on top of this active layer there is PR. They can be or may not be damaged by this etchant, but we don't care because they are thick enough and we can sacrifice them. And now we have two different parts, hard mask and silicon dioxide. However, in our assumption, we assume that in reality, silicon nitride layer has a lower etch rate, so these parts are not etched quite fast, slow etch rate. And instead, this one, green one, is regarded as silicon dioxide one. It is quickly removed from our process. So what we can expect is in reality, say that, let me just draw this one. now let's say this is hard mask, and say this is corresponding to silicon dioxide. And if we perform the realistic etching process, and now let's say that it's gone, silicon dioxide is gone, starting from this top to bottom. However, silicon nitride is also etched slightly, so we will have this smaller step compared with the previous one, and they are uniformly silicon nitride. That will be the case when they have different etch rate, and that is the realistic case. But unfortunately, as all of you guys understand, right now there is no way for me to introduce different etch rate for different materials. So material selection is just done in a binary way. This material is selected, then it is etched, and this material is not selected, then it is not etched completely. So that's the reason why here I assume both of silicon dioxide and silicon nitride are etched in a same etching rate. Then what will happen? Then now we will have much deeper silicon nitride etch profile by using this constant, the same etch rate. So that is the reason why when you have a look at this etched pattern, you can find that this silicon nitride has quite a deep trench here, corresponding to the original thickness of our this side wall thickness. But in reality, it's not the case, and it seems that instead of this kind of huge variation, but we will have slight variation shown here, and that will be the case. It is not perfectly uniform, flat, but the difference is not that much. But for a while, just to understand the limitation of our current implementation of Ångström craft. And anyway, by doing so, now we have anyway this form. Then you can ask me the question, previously we had PR, photoresistor. What is it? Where can you find the PR? At the end of this structure, of course, etching is over, then we have to completely remove this PR pattern. So that's the reason why in this final structure we don't have any PR in it. So of course, before this one, if we stop here, not stop there, then of course we will have well formulated active resin made of PR on top of it. So please do your own exercise so you can check it. So now, so you understand, although we have a very unrealistic group of our silicon nitride hard mask, but in reality the group is not that much, and anyway we have a certain surface of hard mask, and on top of it, well, anyway we have a well defined, uniformly defined remaining pattern that is the seed for our fin patterning. So then later, now we can etch only silicon nitride. Of course, once again you can ask me this question, is there any material who can selectively etch silicon nitride and keep silicon dioxide? Yes, we can find those etchants, And especially important one is we have to do it in an anisotropic way. If we do isotropic etching for this case, then obviously the region underneath this silicon dioxide layer will be damaged. However, if we use just anisotropic etching with this silicon dioxide pattern as a mask, then we can find this kind of pattern. Okay, now previously that this part was filled with silicon nitride previously, but that is gone, and only the part underneath this silicon dioxide layer was saved because our etching was really anisotropic, and this one saved our this hard mask patterning. Of course, another question is, now you say that silicon dioxide is just left here as a mask. However, unfortunately, the selectivity between silicon nitride and silicon dioxide is not exactly 1:0. If you have a certain etchant which can etch your silicon nitride, then usually you have about etch rate corresponding to that of silicon nitride or that of silicon nitride. This is the usual rate or usual selectivity between silicon nitride and silicon dioxide. Simply speaking, in reality, starting from this relatively tall silicon dioxide case, but after etching is over, then maybe we will have this relatively short remaining silicon dioxide pattern. But anyway, it's okay. We have already achieved this patterning. The pattern transferred to our hard mask. After that, anyhow, this silicon dioxide layer can be safely removed, and we will have a final pattern shown here. So let me just summarize what we have done up to now. Previously, in the previous lecture, we just introduced so-called self-aligned double patterning as a simplified form of self-aligned quadruple patterning. In reality, we have to do self-aligned quadruple patterning, do it twice. But anyway, the main point is first make a certain structure, certain pattern with longer wavelengths, and by introducing sidewall formation and use that sidewall as the real pattern we will use. That was covered in our lecture 7. And today's lecture, we just thought about how can we transfer this silicon dioxide pattern onto silicon nitride pattern. So at the first thought, it is quite easy just to use this silicon dioxide one as just a mask and just drill down. But point was, we have to do also here active patterning, because if we have no active patterning, then there can be a problem. So let me just explain the problem we can expect out of this remaining fin. Let's say that fins are remaining even for this part, not removed or not blocked. Then what will happen? Let's say that this will be eventually an inverter. And let's say that there is another inverter, the place for the neighboring inverter. And how can we implement this neighboring inverter? Also using these 3 fins for this P-pad and these 3 fins for our N-pad. And if we do not remove them, then actually they are physically connected. So therefore the information shown here can be transferred to this one. That is not we wanted to have. What we wanted to have is just to process our information only inside this inverter separated logic gate and send it to our metal layer, and through this metal layer just to transfer this information to the next one. After that, from this metal layer, once again the information comes down to our silicon layer. That is what we do in reality for circuit realization. So silicon should not communicate to each other otherwise intended. I mean that. However, if we have a fin, then they are physically connected and they can conduct a certain current or potentials can be shared. That is quite a bad situation, so that's the reason why we have to isolate each individual active reasons. So that was done here. So here, after that, we just transfer our pattern onto now hard mask. The final structure looks quite beautiful. Seems like just a flat silicon one, and only for places we wanted to have fins, we have a very shallow pad oxide, and on top of it we have a very tall hard mask. In order to get this form or this wanted shape, we had to perform quite a lot of patterning, etching, deposition. So what I wanted to deliver to you is, although it is quite easy to say do something, do pattern, do etching, but actually it is involved with quite a lot of intermediate steps. And another one is, although I'm trying to showing some important procedures, but almost every time we do something, then almost every time it is related with cleaning. If we etch something, then in our process emulation, we just say that etch seems to be perfect and nothing left. But in reality, there can be many residual materials on the wafer surface, so therefore always we have to clean the processed wafer completely. So otherwise defects will be introduced in our system. So please understand the real case has a lot more internal steps, but we are just talking about the representative ones. Well, now we are quite happy to have this patterned hard mask. Then you may think that the later part is quite straightforward. Now we can also once again etch the silicon part with this hard mask. Yes, that was my first initial thought, but when I have a look at literature, the next part is called as fin reveal. Means that where can you find sorry about that. So that was, I made mistakes. So in the next lecture we will talk about fin patterning, final fin patterning, and also we will talk about fin reveal. But fin reveal is not that also straightforward, and we will just talk about simplified version of it, because I tried, but fail to reproduce it within our capability. So I will just discuss it later in the next lecture. Okay, then let me just give you homework number 8 and wrap up our today's lecture. Please submit your report by Wednesday morning before we start our lecture. So it is quite simple. You just follow every steps shown here and make your own exercise and try to make this beautiful graphs shown here. I just attached almost every code snippet here. Then what you have to do is just type this one without typo. So if you make any typo, then it will complain. So my suggestion is don't be too ambitious on this code. This code has many disadvantages. One is if you give it a long name, then it does not complain. It's silently neglected. One example is here we have a thickness, but if you write down thickness, then what will happen? So silently it neglects thickness, and thickness is taken as its default value, just number 1. So then maybe you feel that, oh, I just gave the correct statement, but why it behave quite strangely? That is the reason. So please, this code is quite weak against typo, so please do not make any typo. And another one is, yes, it takes some time. So right now it is quite fast, but later you will have long lines of your comment, etching depot pattern. So if you fail at some point, then you have to redo the entire procedure again and again. So please do not too ambitious on your typing. Always try, for example, only try up to here, and if it works,